Hello, I'm Hyunsub, a PhD student at UNIST. Thank you to everyone who attended here. A few days ago, I finished doctoral dissertation defense. I'm planning to do postdoctoral work under the guidance of Professor Semno. Let's start my presentation. The title of our paper is First Responder, Percent Memory Simultaneously as High Performance Buffer Cache and Storage. Today's presentation will proceed in the following order. Introduction and motivation. Percent memory is a next-generation memory technology that has non-volatility, byte addressability, and DM-like latency. Nowadays, commercialized percent memory products such as Intel obtained DC PMM is used by many research groups. The following figure shows the evolution of critical path as the storage device changes. Critical path is a process that can ensure that the data of write request is written completely and correctly on the target storage media. The biggest issue of this study is how to implement the critical path in the environment where the PM is used as a medium for storing percent data. In traditional critical path, there are some unfortunate parts in order to achieve PM's natural performance. Multi-versioning mechanism, long I/O stack, and management overhead, etc. Since the PM is very fast, the software overhead of critical path will become more prominent. In order to guarantee PM's natural performance, this software overhead must be hidden. Many research groups are trying to use PM as a storage device. The study of designing a new file system for PM storage was most actively conducted. These new file systems include PM-aware file systems and tiered PM file systems. Many PM-only file systems and tiered PM file systems have been published in major academic conferences. In the Linux kernel, DAX interface is provided to developers who want to implement a PM-dedicated file system. However, in this environment, it is difficult to utilize media such as hard and SSD that have been used widely. We believe that it is still unreasonable to let PM take charge of the entire storage device. In addition, we cannot use existing file systems that have matured over time. The newly created PM-only file systems will take a long time to be commercialized. We now present the proposed first responder in our paper. First responder is PM-based cache-like layer within the I/O stack. An important thing is that FR not only acts as a cache but also acts as a storage using its percent properties. We compare and evaluate the performance of the two roles of FR in the later evaluation part. Goals are as follows. First of all, our technology can use the existing file system and the existing storage media. FR is implemented in VFS layer. The implementation for FR does not invade the file system part. This means that any file system can easily use FR. Derivatively, being able to use any file system makes all the media they use available. For applying FR, only about 100 lines of code were modified and added in VFS and file system layers. Second, it is necessary to guarantee the PM's natural performance. It requires a quick response and should hide the overhead of the existing I/O stack. Since FR is located in the VFS layer and processes requests immediately, the requirements just mentioned are solved naturally. Also, FR supports in-order file system semantics brought up by PM. In-order file system semantics is where all file system operations occur in the exact order in which they are executed. In order to provide higher performance, the traditional dynamic management system needs to be changed to static management system. As shown in these tables, we can observe that the overhead of the dynamic algorithms can be orders of magnitude higher than that of the static algorithms. This software overhead is profound on faster devices like PM. In order to provide the ultimate PM performance, we select the static mechanism as main algorithm of FR. Finally, durability and consistency should be ensured. The static management we provide naturally fulfills this. Design of FR. This figure shows the internal components of FR. FR is implemented as a continuous combination of chunk and tag. A chunk is a place where actual data is stored, and a tag is a place where some files information and the status of chunk are stored. You can see that the chunk and tag sequencing is divided in two ways. The reason for this design is to facilitate the processing of the updated operation. Additional space is required for the outplace update of the operation. In this two-way structure, the space to contain the updating data can be easily accessed. In terms of utilization, you can think that only half of the entire space can be used as the valid area. However, the two-way scheme is designed not only for updating but also for data from other files. The main elements of tag are key and status flag. The key is a unique value given when the file is created and is used to assign the initial chunk location for each file. The status flag indicates the status of the chunk and consists of a valid bit and a new bit. FR designed with a static management scheme. Every files have a destined location within FR. Not all files are assigned a location by an allocator, but the location specified at the time the file is created. Unfortunately, the environment where files are statically located can result in high miss rate and collision. As you can see in the top of figure, collision occurs when different files share the same chunk. However, there will be very few collisions in FR because FR is large enough than the working set of application. Luckily, we can now get a very large commercialized PM system. We believe that the PM is sufficiently large to hold entire working set of application. In addition, we provide two techniques to prevent collisions due to overlap between data in FR. That's stride and periodic flush. Stride technique eliminates invasion in chunk as much as possible. As shown in red rectangle or figure, through stride technique, files are positioned apart from each other. Then, periodic flush technique can reduce collision penalty. When collision occurs, if a chunk already is cleaned, there is no collision penalty. After data is written in FR, this technique cleans the chunk by immediate flushing in background. This is data consistency protocol for managing data in FR. The following figures show the processes when a data request is performed. A detailed description will be omitted. The core philosophy of the data consistency protocol is that all processes are performed by a static mechanism. Please refer to the paper for more details. From now on, I will show the performance evaluation for FR. The system configuration is as follows. In order to evaluate the performance of FR, we set up 5 comparison groups. FR-X indicates Ext4 with FR applied. X indicates the period value of periodic flush technique. Then we use Ext4, DMWC, DAX, and NOVA for comparative evaluation. First, we perform an assessment of FR's role as storage. Firebench and RocksDB-based YCSB workload were used as benchmark programs. The above graphs show the evaluation of FR performance in an environment in which the backing storage is configured with SATA SSD. Let's see the Firebench results. In VARMAIL and OLTP workloads that frequently generate fsync, FR shows significantly higher performance than ext4 and DMWC. In addition, FR performance seems almost close to NOVA. The following are the YCSB workloads. FR and PM-aware file systems show similar performance. ext4 and DMWC show poor performance in A, B, and C workloads. We emphasize that neither ext4 nor DMWC guarantee in-order semantics. These figures show the performance of a select group of workloads when we vary the PM size, reducing it by half for each point to the left for the various schemes. All performance numbers are normalized to the FR results at 128 GB FR size. The overall trend for FR, ext4, and DMWC are similar, though the drop in performance for FR is slightly greater. NOVA and DAX do not work in environments where the workload size is larger than the PM storage size. There are other interesting results discussed in the paper, but that we omit in this presentation due to time. Next, we evaluate the performance of FR as a cache. Before presenting the results of the experiment, we first mentioned the experimental environment we considered. We wanted to conduct a performance evaluation in an environment that could represent a real world. However, conventional standard workloads does not capture the dynamics of real-world workloads. As shown in above figures, working set of standard workload does not change with time. Also, there is no change in the access intensities of working set over time. To evaluate FR as a cache, we create a new dynamic workload representing real world. Dynamic workload is a synthetic workload generated using FIO, which is an I/O testing tool. Using FIO, we generate 21 distinct files using the characteristics shown in this table A. Total dataset size is 154 GB. We create FIO6 and FIO12 workloads by combining files with different characteristics. The approximate working set sizes for each workload are 50 GB and 100 GB respectively, and the total I/O size for both workloads is 575 GB. Figure B shows how the working set of FIO12 changes, where the y-axis represents all locations accessed per file with time on the x-axis. After the dataset is created, we can see that the maximum working set size is about 100 GB. This is the result. The results show that FR provides more than 9 times higher aggregate throughput and ended over 3 times faster than ext4, despite the fact that FR is providing immediately durable in-order semantics. NOVA and DAX do not work in environments where the workload size is larger than the PM storage size. Conclusion. We presented the first responder, PM-based cache-like layer. FR shares the goal of all PM-based file systems in exploring the performance benefits of PM as a storage device. What makes it unique is that it is an approach that uses an existing modern file systems. Finally, FR ensures durability and consistency through protocol implemented naturally from static management. This is the end of my presentation. Once again, thank you to everyone who attended here. Any question?